this lecture, and I hope this recording will stay for a while. And anyway, so we'll move to 4.3. Section that deals with all these multiplications and divisions and additions and subtractions. Well, I guess last time I told you that I'm not gonna worry much about the multiplications and divisions. So if you just add and subtract, that's already good enough, I think. It looks like exercise 11 from page 4.3 wants us to deal with two numbers that are in a base of 7. So we actually want to add two numbers in the base of 7. Okay, so in the base of 7, we'll be working with powers of 7. That's one thing to realize. The other good thing to realize that in the base 7, we have digits from actually 0 through 6. So 7 already stands for 1 and 0 next to it. So anyways, let's add the digits in a base 7, and we always start with the last digits with 2 and 4. So adding those, I get 6. And notice 6 is the digit in the base 7, so we're fine with that. So once you hit something bigger than 6, like 7, 8, and so forth, it's not going to be possible, so you need to convert it. So far, when I add 3 and 0, 3 is also among allowed digits. So I successfully add these, but then I get a problem because I add 2 6s and I get 12. So now I need to do analogous process to the exercise I just performed, but to write 12 in the base 7. So how do I write it in the base 7? Well, analogous procedure to the previous problem, we care about powers of 7, and those be 0 power and first. So now I need to see how many 7s and how many 1s will fit into 12. Well, you start with the larger, with 7, and you see there is 1 7, right? Plus what remains will be 5, right? 7 plus 5 is 12. So it'll be 1 7 and 5 1s. So the number looks like 1 5, but in the base 7. So how to write this 1 5? Well, standard way, you put last digit, which is 5, and you carry first digit, which is 1. So we just keep adding here. And looks like I get stuck once again, because when I produce the next digit, 1 plus 4, 5, another 5, so I get 10. So I cannot write this in a base 7. I must, it's in base 10. So I must write this in a base 7. And again, I do analogous procedure. I see there is 1 and 3, right? Because I have in the base 7, how many 7s? 1 7 and 3 1s remain. Okay, so the number in the base 7 will look like 1 3. And as usual, I put down the last digit 3 and carry first digit. And add it with what we have in front. And in front we have another 1, so I add and I get 2. 2 is allowed digit in the base 7, right? From 0 to 6, so I just copy it and we're done. So we performed addition in a base 7. Yeah, these things are unusual, and if you do not redo problems that we do in class for a few days, you're probably going to forget all that. So the advice is redo the same problems again. They're awesome exercises. I think they're very good practice problems, because eventually we're going to have a midterm exam, and I promise to give you just one exercise, well, 2 on the midterm, but 1 will come from this chapter. We'll talk about this when we get closer to midterm. In fact, right now we're finishing week 2. So midterm will be, I believe, on the week 4. I need to double check. So a week before, we'll talk about midterm, and I'll give you practice. And yes, there'll be one problem from this chapter. I will give you a good concentration of what type of problem that be. But for now, the advice is just redo this, finish up with homework on this chapter. And I would say this is the last section really for homework, right? So just keep working on it. And now I guess it's a good time to actually take a look at that problem we had for a quiz, right? That problem we had was exercise number 3, I believe. So in exercise 3, you had to add numbers in the base 2. So in the base 2, we have only 2 digits, 0 and 1. Okay. In the base 7, we have 7 digits, 0 through 7. So there is no 2 here. So when I add the last 2 digits, 1 and 1, I should get 2, but in the base 2, there is no such a digit. So what's in the base 2? I say, Alex, only 0 and 1. So we break the number with powers of 2 because we're in the base 2. And looks like the 2, I need to write as 1, 2, because 2 fits in it. This first power of 2 fits in it perfectly, right? So it fits once. And 0 remains. So nothing remains for place of 2 to the power of 0 or for place of ones, right? So 0 ones. And this means that we have those digits 1 and 0. That's how we write 2 in the base 2. And you put down 0, right? The last digit always, and then first digit you carry over for the next addition. So now I do next addition, I add these 3 ones, so it'd be 3. But again, I need to write it in the base 2, and looks like 2 fits in it once, right? And 1 will remain. So we break it with powers of 2. So first power of 2 fits once, and 0 power of 2 will remain with coefficient 1. So this looks like 1 and 1 in the base 2. It looks like that's what I have to write because I put down last digit 1 and then carry another 1, but there is nothing to add it with, so I just copy it. So we have 1, 1, 0 in the base 2. And most people in class did it absolutely correctly. So I was very happy. I'm glad that you do these problems correctly. I would say that for today, I guess I'm not going to be giving you a quiz because we have a long weekend. So I'm more than impressed that you made to class today, in spite of the fact that we have a long weekend anyway. So I'm not going to give you a quiz at the end. It's the best I can do to get you into holiday spirit. We have a long weekend, right? But I'd like to talk a little bit about next chapter just to give a slight introduction. And I would say that next chapter will make people much happier, because this is way more familiar stuff compared to these different basis stories. We definitely don't see much of it in the real life unless you become a computer programmer or Egyptologist, then you deal with this unusual ways to write numbers. But next chapter, which is chapter 5 here, starts to talk about things that are already very familiar. So let me clean my board and say a few words about chapter 5 that talks about a set of so-called natural numbers. You can see this number set that we usually utilize to count subjects, such as we start with 1, 2, 3, and it continues forever, right? So you can keep counting and counting, and it goes infinitely. So there is a special name for this set of natural numbers. It's like a capital N with a thicker bar that goes across. And well, it's good to be familiar with the fact that when someone says, find a natural number, it means it's one of these positive whole numbers, no fractions in the set. So numbers we use to count subjects. So I guess this chapter brings you with some vocabulary, and one should realize what natural number means, right? So then they talk about timetable, basically. So how you factor various numbers such as 24. And if you ever did factoring exercises, I'm sure you will recognize these ideas. So you always start with 1. You see if it works, and 1 always works. Then you try 2. Well, for even numbers, 2 also work, 2 times 12. Notice that 24 is an amazing number. It has so many factors. So you start with 1, try 1, then 2, then 3, then 4, then 5. Notice that 5 is not a friend of 24. 5 is not working. Okay, so you skip it and go to 6. Then you try 7, and you see that 7 doesn't work. And notice that you don't really have to continue, because if you went so-called halfway through, in other words, if you already have 6 tried, and 6 times 6 is already bigger than 24, right? Because it's 36. It means you went halfway through. What does that mean? Well, if you be able to factor it with, again, with the bigger factor, then the factoring repeats. Like here, we have 4 times 6 and then 6 times 4. So you repeat. So now you go down on the smaller one and increase the larger one. So you basically flip this factor. So 8 on first and 3 on second. So you just repeated that, and then you repeat this, and then you repeat that. So technically, last 4 factorings are pretty much same as first 4, right? You factor with same numbers, but you just flip them around so you commute, people say, around the multiplication sign. Okay, so that's the way it works, I guess, and looks like they consider in various factorings here in this little chapter. There is another notation in here. If you can divide one number by the other, we say number is divisible. So what does that mean? How can you write it? Well, you can write this with a bar so that 24 could be divided by 8. So instead of saying word is divisible by, you use this little bar. You say, Alex, what if I just say it is divisible by 8? That's fine with me. I will understand. I'm not going to pick on you if you didn't write it like that, because I know it's a little bit unusual notation. It is used in number theory. So if you ever take that class, then, well, you'll see it. But 24 is divisible, means you can divide 24 by 8. Just like that. Now, if 13 is not divisible, then, well, you cannot really divide, so they cross out this little thing. In fact, looks like we can write this not like that, but 8 could be divided by 24. Divided into 24. See, it's like that. So you can say 12 could be divided into 24. So we put smaller number first. That's the idea. Smaller number first. So the idea is factoring, but this divisibility is a little extra this section brings us with. So that bar means the number could be divided into those. So how can we check this out? Well, you could just use a calculator. I guess that's the simplest way to check. So if they say is 4 a factor of that big number, well, what you can do is get yourself a calculator, take that number, but I better write it down because otherwise I lose it, right? So write it. So this is 4 going to be a factor of 3,754,086. Yes or no? Well, let us divide. So I take that 3,754. That's a big number, right? And then 0.86. and divide it by 4. And the answer is no, because it didn't divide. So the answer is no, or some people will say just cross this thing out, but this is yes or no question. So they wanted to hear if that's divisible or not. And that's what they say. So it looks like the last digits are not divisible. So the statement is false. I said, but how did they get to it that quickly? Well, it turns out they used a special divisibility test. So in order to actually check this out, all you care about is if last 2 digits you can divide by 4. You say, why is that? Well, you can split this number into 3, 7, 5, 4, 0, 0, 0, plus 86. So the point of story, if you have the first part, then you can definitely divide by 4. The first part. I say, why can't I divide this by 4? Well, because you could split this number as a factoring of the first part without zeros. So notice that this 2 zeros means times 100, right? And what's before? And before we get that 3, 7, 5, 4, 0. So once you factor this with first part and then those 2 zeros, notice that 100 is 4 times 25. The point of story that since you can factor with 4 part of your number, then the rest will be a product of whatever, 25 and the rest, and it'll be times 4, so you can divide it by 4. So that's why when you test divisibility by 4, you just care for last 2 digits. And the last 2 digits, the question is, can I divide 86 by 4? No, because if you had 88, you'd be able to divide by 4, right? Or 82, but not 86. Can divide by 4. Divide by 4. So they actually use that special test. That, well, yeah, there's some people just memorize and say, oh, so if I want to divide number by 4, I have to be able to divide last 2 digits by 4. And I say, Alex, why don't you just take calculator and divide it by 4 and that's it? But yeah, that was what I did right away. But they want to have this special test considered. So I just today want to talk about example 1, the other 2 parts of it, the other tests that they provide us with. And turns out the next test analogous will be in the part C. So I'll look at A and then C, and then we'll talk about B. So it turns out that in the part C, we have something very similar to test of divisibility by 4. Please notice that both of these numbers you can also divide by 2 because last digit is even, right? So by 2 you can divide, but turns out by 4 you need to be able to deal with 2 digits. Well, analogously for divisibility by 8, you need to look at last 3 digits. So if you be able to divide by 8, that should be last 3 digits that you can divide by 8. And if you see that this is indeed a true statement, so notice that 840 you can divide by 8, and that's analogous test. So if you split your number 677 840 as a sum of 2 pieces, so it'll be 677 with 3 zeros plus 840. So the whole point of this story is that if you divide by 8, if you can, the original number, then the sum of these two, you should also be able to divide by 8 and last and first. And notice that first number that consists of factoring 677 multiplied by 1,000. The 1,000 you can factor with 8 because each 10 is 2 times 5. So it will be actually 8 times 125. So all you care about is this number, if you can divide by 8. So the first factor can divide by 8. So can you divide by 8 the second one? And well, you just go ahead and divide, and looks like 840 you can divide by 8 because it's 800 you can divide by 8, and 40 it's 8 times 5. So if you say yes, you can divide the last 3 digits by 8, then this whole thing you divide by 8 because 677 with 3 zeros automatically divides by 8 because this factors with 8 and 125 and 677. So the only concern is last 3 digits. So see how those tests with 2, 4, 8 go. For 2, you check the last digit if you can divide it by 2. For 4, you check last 2 digits. And for 8, you check last 3 digits, and so forth. But of course, it takes a while. So one could say, just Alex, take calculator, divide by 8, it's fast. I know. But I'm here just to explain what they're talking about. Please notice that in the part B, you cannot divide by 2 because it's not even number. So you can see that previous tests do not apply because that's an odd number. So the odd numbers you cannot really divide by 2, right? Because they're odd. We can try. You're gonna get some results. Okay, that's good that you made it. No problem. So looks like we have actually a question about dividing the number by 9. And what they do is they show you a test. So what you do is add all of the digits, like 4, 1, and so forth, and you get 36. And turns out the sum is divisible by 9. So you can divide this by 9. By the way, if you can divide by 9, then you can also divide by 3, right? Because 9 is 3 times 3. But notice what they say here. They say you cannot divide it by 9. So this is wrong. This is no, because you can. See, they trying to trick us. They say, no, we cannot divide this by 9, but we can. So we say, no, we can. So that's kind of odd question, right? They switched it around. But I guess it's okay. I guess that's the whole point of story. So it looks like in this chapter, we'll care about factoring. We'll do some factoring stuff here. So what I can do is go to the end of the where the exercises are, end of 5.1. And you can, if you feel like it, if you're already done with your homework for chapter 4, and if you feel like doing some problems in advance, you can do the print screen of this homework. Notice there is not much, just 1 page, right? So it goes up to 57. So you can just let you go with 57. Let me clear this so you can do the print screen if you want. Because I'm sure that these things you already encountered back when you took various algebra classes, if you took any, of course, and I'm sure most people did it. So here they talk about this divisibilities, and then they talk about factorings, and then, well, the rest, the greatest common factor, that's something that I'll talk about next time. But looks like the main issue is that divisibility stuff, so you could just try some problems. And definitely it needs to be continued, expanded, and it will be on Wednesday, because Monday we don't have a class, remember? It's a holiday. And in a holiday spirit today, I decided to let you go a little earlier so you can feel that that's something I think important. And I'll see you on Wednesday. So Monday, no class. I'm gonna stop to record at this stage. Again, I hope